So this is currently week 8. Week 11 will be your exam. Same deal. That means that your exam, you can expect that week 8, 9, 10. So it'll be on April Fool's Day. So most of the day, oh, nuts. That's going to actually be a bit of a pain. Hold on. I think that's, actually, wait. Okay. So first off, Ramadan ends, okay, March 18. So that we're going to be in the clear for that. But Pesach is the evening of. I couldn't remember if it was Erev Pesach or day 1 Pesach. So that means that if you're doing the fast of the firstborn, then speak to me. But otherwise, that shouldn't really be much of an issue. Okay? Right? If there's some but because that's the evening of, that'll be fine. That most likely means that Tuesday, I'll be deciding as to probably be doing, I might end up doing that over Zoom, since it is a holiday. We'll see. And of course that we will I will give a practice exam and I will send that out like on the 24th, and we'll do a review on the 31st or the 26th, depending on timing for it. So topics for the second exam are fairly straightforward. We will go all the way through hash tables, but only one question worth 10 points will be on hash tables, and then there might be a 5-point analysis question on hash tables. So you'll be in the clear for that. The vast majority of exam 2 covers this, which is, wait, no, this is 1051. This class isn't 1051. That's the 1051 course I had pulled up. All right. Obviously, my brain still wants to be on break. Okay. The vast majority of the exam will be on recursion, trees, heaps. Yeah, recursion and trees. There's not going to be much in the way of independent recursion questions because most of the tree questions, they become a lot easier once you do recursion. Okay, so the vast majority of the exam is on trees. Note that you do not have any homework for heaps, right? Notice that we have these tree videos and then you have heaps. You don't get to skip over this. This is going to be on the exam. It's just it's not worth making its own assignment about. I've done that before. It just adds in an extra assignment and adds just a bit too much to do in the semester. So you'll want to watch these videos because it does cover this nifty data structure called priority queues. Obviously, though, that we aren't there yet because you still have the tree videos and the index tree is due March 20th, which is what I'm planning on going over today. And I know plenty of you are still working on the recursion, which is still not yet due. So if it sounds like I'm speeding ahead, that's because, again, a lot of you will end up like in this spread of stuff, depending on how easy or hard you find these assignments, okay? So, yeah, then the heap videos will be there. Cheater's Hangman is going to be the last big problem. It's your 200-point problem. It's both the most complex problem I give, but also one of the most fun ones because you're making a version of Hangman that's going to cheat in the background so that you can give it to your roommates or your friends and they'll play Hangman and they'll have the hardest time ever winning. It's pretty funny. And if you prefer, you can do a version of Wordle that does this instead because it does the exact same algorithm. It just is presenting it in a different manner. Anyway, but yeah, the vast majority of this is trees and that. The index tree is pretty interesting because I give you an index node, I give you an index tree. The code is actually very straightforward to do. The hardest part about it is just kind of figuring out, oh, this is how I do file reading and build this entire thing. What makes it weird is that, right, I know you probably haven't hit trees yet, but think of basically a tree being similar to a linked list in the sense that we have nodes, right? What makes the index tree a bit weird is that each node is going to also have as its item, rather than just like a single thing, it's going to have a list. So it's a data structure where each item is another data structure, and that can be a bit weird. What you're looking at is basically saying, hey, every node represents a word, and it also keeps track of all the lines it found that word on. That's the data structure you're building. Now, the reason I haven't replaced this with the more standardized red-black tree, okay? The more standardized red-black tree, which is the common pedagogical thing, made in 1978. It's a self-balancing binary tree. And it's called red-black because you color these nodes a certain color, and then you follow 5 rules, which gives you 5 cases for adding and removing to help you self-balance the tree so that your runtimes always are log of n, okay? Which I'll go over into how you actually read log of n on Thursday, okay? These have self-balancing. They've been done for a while. You can find the code online. It's right. Pseudocode is like right here on this is like C. This is like C. Yeah, the C code right over here. The reason I don't do this is not because it's not interesting, but because I like giving you problems that you're going to experience in real life. You're obviously not going to be building an index tree in real life. What you are going to be dealing with is files like pg100.txt, which is the complete work of William Shakespeare, okay? Nothing too exciting other than it's a quote-unquote big file. And you might be thinking, oh, how big is big? It's just text. And you're right, it's not actually all that big. It is a couple megabytes. But it turns out that a couple megabytes is enough to make a lot of text editors and terminals just choke. So one of the issues we have with index tree, which is a deliberate issue that I'm inflicting upon you, is you'll be like, okay, I'm running this, but I don't see all the words, right? My output does not include all the words. It only has all the ones from lowercase m and forward. And that is because your console, be it on the terminal or in your IDE or in VS Code, your editor, it will only have as a default a certain number of lines it will keep in its memory. And when that fills up, it will just discard those. And that rarely comes up until you're printing out thousands of lines, which you will be doing because there's thousands of different words. So you'll either just have to be aware of that. You can always write it out to a file. You can always change the settings in your IDE. But the reason I do this is because this is a real problem you will experience where you're printing out too much stuff and your log is suddenly too big, right? Or your console's suddenly too big. And that's just a deliberate thing. You will see this happen when you open files in an editor as well, where the editor will warn you, hey, this file is too big to do our analysis on, to do syntax highlighting, right? And so if you try opening like a 50 megabyte XML file or something like that. So that is the context of this problem. It is a good problem, but I found that it has these unintentional kind of issues, which are good real life issues that I want you to experience. It's part of the reason why we send kids to elementary school anyway, and stuff like that. As I explained to my son, as I was talking about with my son's, team at his school. It's like, we could ostensibly homeschool the kid and he'd do fine academically, but school's a safe place to learn social friction, elementary school and that kind of thing. Whereas here, these assignments are a safe place to learn these kind of real life issues that might cause issues for you on an actual job. That's my philosophy for some of these problems anyway. Now, going back to our other assignments, the one that's more recently doing, the 8 queens problem. Remember, you only have to do one of the 2 chess problems, okay? So one of the 2 chess problems. Come on, you can do it. I don't know why it's not high. There we go. And I want to talk about the 8 queens problem for a minute. Okay? The 8 queens problem is not that bad of a problem. Let's go open up Paint. Okay? First off, 8 queens problem over here, you'll want to start by implementing this function, okay? This function I give you, this pseudocode. Here, the board is your integer array, okay? It's a 2x2 integer array. You pass it in. Some people prefer to keep it as a static value, and that's fine. And then your position in this case is going to be the column, because you want to put 8 queens, 1 per column, right? Make sense? Want to put 8 queens, you need to put 1 per column, and you're essentially going to move left to right. And your choice in this puzzle is, what row am I going to put the queen in? Make sense? So if you're out of bounds, right, if your column is 8 or more, return true. For each possible row, for each possible choice, in this case, which row, check if that row is valid. When you're just starting out, what you want to do is say, hey, this function, valid choice, is always going to return true when you're just starting out. Why? So you can make sure the recursion's working. And you'll simply put the queen at that point, and then you'll do this this bit over here exactly as written, which is go to the next column essentially, and check if that gets you true. Now, the actual main part of the work is doing the valid function. With a queen, we have a few things that, let's take a look at our queen. Our queen can move, isn't she beautiful? She can move in 8 directions, right? Up, down, left, right, as well as her diagonals, because she's both a rook and a bishop. All right? Now, does that mean that when I'm checking if I'm plating a queen down, do I have to check all 8 of these directions? You certainly could, but you don't have to. We can actually cleverly eliminate some of these from our evaluation. So, first off, we are always placing queens from column 0 to column 8. We are going this direction, left to right. That means, and whenever we hit a dead end, we always pick up any queen we just placed down before we move back, before we backtrack. That means there's never going to be any queens to the right of us, right? All the queens that we place are going to be so all the queens we have to look for are queens that have already been placed, which means they're behind us, which means they're to the left. So we don't have to check any of these directions, right? Make sense? We don't have to check any of the direct queens to the right because there aren't any there yet. Similarly, we're enforcing that we can only place 1 queen per column, which means that there should never be any queens above us or below us. That only leaves 3 directions. To the left, our upper left diagonal, and our lower left diagonal. So this is going to be fairly easy to check. And what I recommend for us is we do a bit of code that may look a bit weird for us. This is actually, and normally I wouldn't necessarily go into this much detail, but it's after spring break. You need a bit of help getting your gears going. I know I certainly do. Okay, so what a lot of us would like maybe. So I always like to write my for loops as simply as possible. For int I is equal to 0, and then we have a condition. We'll figure out that condition later. Okay. That's the important part. Leave that condition for later. Okay? And this is just checking back and to the left, right? What we need to check for is, do we see a queen in the same row? So what we're going to ask is if, well, where's the queen going to be currently located? We're going to assume that we're given the row and column. So if board, and then the row, okay, the column is always going to be the same, but the row is going to change. So if col, and what we're going to do is we're going to check board row, and what we'll do is for these parts of the problem, we're going to radiate outwards from where we are. So I'm not writing the full line, A, because I don't have enough room, but B, because this is the important bit over here. If board row minus I, right? Row minus I. So we'll start at where I am, then we'll do row minus 1, row minus 2, row minus 3, row minus 4. If we hit a queen, we're going to return false, right? It's not safe. So board row minus I. Now, how do we make sure we don't go out of bounds? We just simply we use whatever condition is supposed to go here. And that condition is, go ahead and write a special color for that. We'll make sure that we do row minus, here, I will go ahead and row minus I is greater than or equal to 0, right? We're just going to make sure that that row minus I is in the valid range. So even though I is being increased, I don't have to worry about messing with my I at all. I'm just going to go with the standard I is equal to 0, I plus plus. And then as I goes up, this value is going to go down. Yes?
What does it say on that third semicolon? Does it say CFT?
This one?
To the right of the arrow.
Oh, that's I plus plus. I just can't write worth a darn.
Thank you.
That is just I plus plus because, again, not only am I just drawing, I'm drawing with my finger. So, I plus plus. So that's just going to be, and I'm using paint. So it's not exactly the most thing there. Okay. Yeah, so something along the lines of this. So our for loop again will look like this. For int I is equal to 0, I row minus I is less than or equal to, greater than or equal to 0, I plus plus, and then return false is our condition if board row minus I, and we're just gonna actually line this up so that we can kind of see. I think that looks nice in Notepad as best as it can. Okay, if row minus I, column is the same, equals, let's put a 1 for queen or whatever, right? I'll just put queen here for whatever, whatever you put in insert your own queen there, right? If I see that in your code, I know that you didn't listen, you typed what I wrote, but didn't hear what I said. That you put whatever you put in for your symbol for your queen there, okay? Return false. Okay. Now that's for handling what if we have a queen and we're checking this direction, right? But what about checking something like the upper left? Okay. Now, because the row and the column changes, a lot of students say, oh, we are changing the row and we're changing the column, thus we need a nested for loop. No, you don't need a nested for loop, okay? Because the change in the row and the change in the column is the same rate, right? They both increase at the same speed. So you only need one variable, I. The difference here is for doing your upper left and your lower right for this for loop. You can turn this into a compound statement. That's my hint here. That's actually the answer. You can turn this into a compound statement. You can say clause and clause. So you can have two conditions, right? Because there's two ways this can run out of bounds now. This only had one way it could run out of bounds, which was row minus I. This way, when you're going diagonally in either direction, it can go out of bounds in the column direction as well. One happens to be going up, the other happens to be going down, right? So you can make these Boolean statements, these ending conditions for the for loop, as complicated as you need them to be. But I find starting from where my queen, I'm trying to put the queen, and radiating outwards from there, that leads me to the answer, okay? Now, moving on to Sudoku, right? For the Sudoku solve method, I want to be very clear about this. Boolean, right? Public Boolean solve. No. Thank you, Notepad. I don't want you to try to correct what I'm doing, though. Okay, public Boolean solve. We are going for solve. It's very. I see a lot of students do this, where they say, hey, I'm just going to take the Sudoku board, and then what I'm going to do is I'm going to do a for loop inside a for loop inside a for to find the next empty square, and then I'm going to check if that's empty, and then if it's empty, I'm going to go through all the choices for it. You don't want to find your location, okay? You should already know it. That's your position. You always take in your position as an argument. Okay? Make sense? So for int column, int row, int column. It's also possible to feed in something one dimension, a single number, and then take that number and turn it into two variables by just doing some division. But anyway, what we do here is that we basically, since we're going left to right across the screen, we basically check if column is great. Here's our base cases. If column is greater than 0, sorry, not greater than 0. If column is greater than or equal to 9, right? If we've gone out of bounds with the column, then we're going to say column is equal to 0, row plus plus. Make sense? We're going to say, hey, if we're done with the row, we're going to go to the next row, and we're going to start at the beginning of it. If row is greater than or equal to 9, if we're out of rows, then we finish the puzzle and we didn't hit a dead end, which means we're done, which means we have the answer. So return true. Make sense? That's your base case there. So it's a bit more complicated by having two variables, but one of those variables is just kind of basically your progress for one of the other variables. Next, we have two, not one, but two recursive cases. What are those recursive cases? Well, we've hit a square. We're still working on the puzzle. We're at a current square. We're at row column, and there's two possibilities. Either it's empty or it's not empty. If it's not empty, and this is the last bit I'll show. If it's not empty, we do this. If board row, comma, column is not equal to, is not equal to 0, meaning it's not empty, then we are going to just go on to the next row, which we're going to do recursively so that we don't accidentally try changing this square. We're going to return, solve. We're going to say, hey, I've already solved this one, or rather this one's already solved. We're going to solve board row column plus 1. We aren't going to try to manipulate column directly. This is just, the only reason we do this is just kind of to fix it from being out of bounds. Otherwise, we just go with the same algorithm we just learned, our for loop, okay? Now, again, what you're going to want to do is accept valid as true. The hardest part about it is this is the 3x3. If you're having trouble with that, rather than wasting more of your time and going through that, if you have trouble with doing the 3x3, reach out to me. There's some fun math you can do without that. But if you're having trouble with figuring out the 3x3 square, just remember that there's two solutions. There's the math solution, and then you can just use a bunch of, write a grand total of 6 if statements, not nested or anything, just basically saying, hey, if the row is 0, 1, or 2, then the corner is 0. If this corner is 3, 4, or 5, then the corner is 1, right? And you just, otherwise it's the corner, it's not 1, the corner is 3. Otherwise the corner is 6, so it's either 0, 3, or 6. You'll understand when you get there. And so there is a clever solution, but the not clever solution is very efficient and doesn't take that long once you actually write it out. Okay. With that, I'm going to go and help people. If you did not pick up your exam, I should still have it unless you are you, in which case I think the TA has it, unless you've already got it back.